Ever wondered how data is structured and organized in a database? Well, that's where database schemas come into play. Acting as a logical blueprint, a database schema defines the structure, organization, and relationships of data within a database. Think of it as the architecture of a building, outlining the layout and the connections between different parts. Key components of a database schema include tables, columns, constraints, indexes, views, stored procedures, functions, and triggers. Each of these elements plays a crucial role, from the fundamental building blocks of tables and columns to the rules and conditions enforced by constraints. Indexes speed up data retrieval operations, while views, stored procedures, and functions offer ways to simplify complex queries and enhance security. Triggers, on the other hand, automatically execute in response to certain database events. Dive into the world of database schemas and discover how they form the blueprint for data organization and management. Think of tables as the building blocks of a database schema. Imagine a massive library filled with books. Now, these books don't just float around aimlessly, they're organized on shelves. In the world of databases, these shelves are akin to tables. Tables are fundamentally the heart and soul of a database schema. They are the containers that hold related data entities, neatly sorted into rows and columns for easy access and manipulation. Just like how every book has a title, author, and publication date, each table in a database has a structure defined by its columns. These columns, in essence, are the individual data attributes or fields within a table. For instance, in a table storing information about books, columns might include title, author, publication date, genre, and so on. Each column has a name, which is like a label, and a data type, which dictates the kind of data it can store. Data types could range from integers and strings to dates and more. If our author column has a string data type, it could store text data like J.K. Rowling or George R.R. Martin. Columns come with additional properties too. There's nullability, which determines whether a column can store a null value or must always contain data. Then there's the default values, a safety net of sorts, which steps in when no explicit value is provided for a column during data insertion. And finally, we have constraints, the rules of the game. Constraints are conditions that maintain the integrity and consistency of the data in a column. For instance, a constraint might specify that the publication date can't be a future date, or that the genre must always be filled in. In short, tables and columns are like the shelves and books of a library, providing a structured and organized way to store data. They define what data is stored and how it's stored, forming the basic structure of a database. So tables and columns provide the basic structure for storing data in a database. Imagine trying to maintain order without rules. That's where constraints and indexes come in. Constraints are like the traffic signs of your database, enforcing rules on the data to maintain its integrity and consistency. They lay down the law, so to speak, to ensure that your data behaves just the way you want it to. There are several types of constraints, each with its unique role. Primary key constraints ensure each record in your table is as unique as a snowflake. No two records can share the same primary key. Then there are foreign key constraints, the glue holding different tables together. They enforce referential integrity, making sure that the relationship between tables remains intact. Unique constraints are the bouncers at the club, ensuring no duplicate values enter a column. Lastly, check constraints are the vigilant guardians validating data values against specific conditions. Now let's move on to indexes. Picture a library without a catalog system, quite chaotic, right? That's where indexes come into play. They speed up data retrieval operations, making it faster to find the data you need. They're like the catalog system of your library, helping you locate the book you want without having to skim through every shelf. Indexes are created on one or more columns of a table, allowing for faster lookups based on the indexed columns. They're particularly effective for frequently accessed columns or columns involved in joins and search operations. Think of them as shortcuts to your data, enabling your database to skip unnecessary steps and get straight to the point. In essence, constraints and indexes are the unsung heroes of database management. Constraints maintain order, ensuring your data's integrity and consistency, while indexes enhance performance, making data retrieval operations faster and more efficient. They work behind the scenes to optimize your database, making it more reliable and user-friendly. Constraints ensure data integrity, while indexes make data retrieval a breeze. Let's delve into the virtual world of views and the handy helpers, stored procedures and functions. Imagine a window that presents only a portion of the data from a table or multiple tables. This window is what we call a view. Views are virtual tables that don't hold data themselves. Instead, they display data that resides elsewhere in the database, providing a specific perspective of your data. They can simplify complex queries, enforce security policies, and abstract the underlying data structure. Think of views as a tailored presentation of your data, hiding the complexity of your data operations. Now let's move on to stored procedures and functions, two powerful tools in our database toolbox. Stored procedures are precompiled blocks of SQL code that perform a specific task. They're like a recipe, detailing steps to achieve a particular result. For example, you might have a stored procedure to calculate the total sales for the month. On the other hand, functions are similar to stored procedures, but they return a single value. They're like the mathematical functions we all know, where you put something in and get something out. A function could, for instance, calculate the average rating of a product based on customer reviews. Both stored procedures and functions encapsulate business logic and data manipulation operations. This encapsulation enhances security by preventing unauthorized access and modifications. It also promotes modularity, meaning you can reuse the same block of code in multiple places, and performance, because the database can optimize the execution of these pre-compiled code blocks. Moreover, stored procedures and functions can be invoked by applications or other database objects, automating common tasks. For example, an e-commerce app might call a stored procedure to check the inventory and place an order. In summary, views provide a customizable lens to look at your data, while stored procedures and functions act as efficient, secure, and reusable blocks of code that perform specific operations. Views, stored procedures, and functions add layers of efficiency and security to our database. What if you could automate certain operations in response to database events? Enter triggers. These are special types of stored procedures that spring into action, like vigilant guardians of your data, whenever certain database events occur. Picture them as automated bots programmed to perform specific tasks when events such as data insertions, updates, or deletions take place. Now, you might be wondering, why are triggers useful? Well, they serve several key functions. For one, they can enforce business rules that go beyond the standard constraints. Imagine ensuring that a discount is automatically applied on a customer's birthday, or that an inventory count is adjusted the moment a sale is made. Triggers also play a crucial role in auditing. They can be programmed to log changes to data, providing a valuable record of activity. In essence, triggers bring a level of automation and control to the database, enforcing business rules and auditing changes. So, we've taken a journey through the components of a database schema. We started with tables, the fundamental building blocks of any database schema. Each table represents a collection of related data entities, neatly organized into rows and columns. The structure of data is defined by these tables, including the names and types of columns, constraints, and relationships with other tables. We then dived into columns, the individual data attributes or fields within a table. Each column has a name and a data type that defines the kind of data it can store. Columns may have additional properties such as nullability, default values, and constraints. Next, we explored constraints, the rules or conditions enforced on the data to maintain integrity and consistency. Constraints ensure that our data remains unique, maintains referential integrity, and falls within defined validation parameters. We also discussed indexes, which are data structures designed to improve the performance of data retrieval operations. Indexes are created on one or more columns of a table, allowing for faster lookup of data based on the indexed columns. They are like the express lanes of data retrieval, speeding up query performance significantly. Then we touched on views, the virtual tables derived from one or more underlying tables or views. They present a subset of the data or a transformed representation of the data from the underlying tables. Views are like the windows through which we can view our data in simplified or abstracted forms. We also talked about stored procedures and functions, the precompiled blocks of SQL code that perform specific tasks or operations. They encapsulate business logic and data manipulation operations, enhancing security, modularity, and performance. Lastly, we discussed triggers, the special types of stored procedures that automatically execute in response to certain database events. They can enforce business rules, audit changes to data, or implement complex data validation logic. In conclusion, a database schema provides a structured framework for organizing and managing data within a database system. It's like the architect's blueprint for your data, ensuring integrity, consistency, and efficiency. Understanding and properly designing a database schema is crucial for efficient data management. It's the blueprint that guides us in the world of databases.